Department at the Museum of Science. Tonight's lecture kicks off an exciting new year of adult programming at the museum. We are hoping that you've picked up a Brainiacs brochure, hot off the press, which gives a lot of information about the exciting personalities and the innovative new formats that we're going to be trying out this year. So if you didn't get one, please grab one on your way out. Tonight's lecture is presented by the Wright Center for Science Education at Tufts University, and additional support is provided by the Lowell Institute, which enables us to provide the lecture and this lecture and the other lectures via the WGBH Forum Network podcasting. And a link to that may be found on the museum's website, www.mos.org, in the archived lecture section. Tonight's program should last approximately 2 hours, and that will include the audience Q&A. So please silence all your pagers and turn off your cell phones. And if you need to leave during the program, please exit via the rear door rather than coming down to the front. I'm pleased to welcome the host of the Wright Lecture Series, Dr. Eric Chason. Dr. Chason is director of the H. Dudley Wright Center for Innovative Science Education at Tufts University, where he is also research professor of physics and astronomy and research professor of education. He is an associate of the Harvard College Observatory, where he teaches introductory astrophysics, and is also affiliate director of the Massachusetts Space Grant Consortium based at MIT. In addition, Dr. Chason has served on the Museum of Science's Board of Overseers since 2002, and he has a new book coming out next month entitled Epic Evolution. So be sure to keep an eye out in the bookstores for that. So please join me in welcoming Dr. Eric Chason.
Thanks, Lisa. Thank you. Well, thank you very much, Lisa, and thanks to you and to all of the members of the museum staff for once again inviting us back to the museum. This is really a wonderful partnership between the Museum of Science here in Boston and La Fondation Wright de Genève. That's the Wright Foundation in Geneva, Switzerland, whose principal operating arm in the United States is the Wright Center at Tufts University. This lecture series is held in Boston in the odd years and in Geneva in the even years. This year, the theme for the lecture series here in Boston is once again one that's close to my heart, cosmic evolution. You see the arrow of time archetypically and symbolized on the screen in front of you. This will be the theme throughout this series, whereby we bring before you a wide variety of speakers addressing an integrated, interdisciplinary theme. It's a story, it's a narrative, and it's a narrative about ourselves. It's not an anthropocentric story, but it's a story whereby we understand or seek to understand scientifically, with the good empirical information, the origins of galaxies, stars, planets, and people. If I had to define cosmic evolution, I'd simply say it's something like the study of change through time. If you back me into the corner and put the bright lights on me a little more, I'd have to say something like it's the study of all the myriad variable changes throughout the entire history of the universe, developmental changes, environmental evolutionary changes, among all radiation, matter, and life forms. We're trying to, therefore, explore the notion that we might be able to put on the same page the essence of astrophysics and perhaps biochemistry, and bring before you a wide spectrum of speakers, whether they be physicists or biologists or geologists or chemists or anthropologists, etc., and explore a very powerful theme, a theme that was enunciated by Heraclitus 25 centuries ago, and he looked out his window and said, all flows, all fluxes, supposedly said, there's nothing permanent except change. So the emphasis here is on change. We see that change out the window, and we try to explore in a unifying way in this series of lectures over the course of the next many weeks that notion of change, and to explore furthermore, as a working hypothesis in science, whether we can place onto that same page the thread of change, whereby the early particles that we'll hear a little bit about tonight change to become the more substantive building blocks of life. Those building blocks of life, perhaps called atoms, accumulate into the galaxies, about which we'll also hear tonight. How the galaxies spawned the stars, and the stars in turn changed in their hearts to create the heavier elements, the building blocks of life. The building blocks of life became life. Life evolves into the culture and technology that we now share. We'll bring before you not individual speakers, as you might ordinarily hear in the lecture series. A speaker comes in, talks for an hour, everybody goes home. I've done that in this room many times. We do it differently here in the Wright lecture series. We try to do it interactively. We try to bring out, I'll say it later in the panel discussion, the subjective side of science, to invite you into the scientific method and to invite you into the world of science as we're experiencing it. It's not as clear and clean as the textbooks would have you believe. The scientific method is kind of fuzzy. It's kind of emotional at times. There are biases and opinions of individuals, and we'll see those individual interests and opinions in the panel discussion. So tonight we bring before you a couple of outstanding, eminent, world-class authorities in the earlier universe, a particle physicist and an astrophysicist. Next week we'll move on to studies of stars and planets. In a couple of weeks we'll bring before you biologists, one of whom will address the issues of the origins of life, the other of whom will address more advanced developmental and evolutionary stages with regard to more complex life. And then we'll end the series on the fourth evening by kind of making a gesture to the unknown, as I like to say, by bringing before you an anthropologist who will explore the state of the union or state of the planet as it now exists, and then a person speaking about future, where is this all going, speculating in particular this year about the prospects that this arrow of time must apply to every nook and cranny in the universe, and therefore must mean, perhaps, that we're not alone in the universe. So we begin this evening with a pair of wonderful speakers. They will be concentrating on the earlier universe, not entirely at the left in this Big Bang to humankind scenario, because the galaxies are out there now, the particles are out there now. But we'll see as they develop their talks individually that many of the events they're talking about probably occurred naturally more in the earlier universe than currently. And then we'll see how over the course of this story, this narrative of which we are a part, that we're moving from left to right in this particular arrow of time, from simplicity to complexity, from inorganic to organic, from chaos in the old-fashioned Greek sense to order. And we'll want to use this arrow of time as an intellectual backdrop against which we will ask the fundamental questions. Scientifically, who are we? Where did we come from? Where did everything around us come from? The air, the land, the sea, the points of light in the nighttime sky? Why is there, when you look out your window, so much order and structure in the universe, apparently growing in complexity over the course of time, despite the second law of thermodynamics, which prima facie would suggest that maybe some of the stuff ought to be breaking down? Perhaps that will come up in the panel. The speakers will speak for shorter periods of time than normally the case, so that halfway through the program, after we have a 1-minute seventh inning break for you to stretch a bit, we'll form a panel, and then we'll invite you into the world of our dialogue, perhaps using the Socratic method, or perhaps letting you entertain questions back and forth by challenging the speakers. But let's go to our first speaker straight away. One of the most eminent physicists on the planet today, Frank Wilczek, is this year's current Nobel laureate in physics. He began his career at Chicago, moved on to Princeton, where he took his PhD at a rather young age, 21 or 22, something like that. Spent time teaching at Princeton, Santa Barbara. Spent a good chunk of his career at the Institute for Advanced Study at Princeton, where he was eventually the Oppenheimer professor. And now, for the last several years, he's come to MIT to become the Hermann Feshbach Professor of Physics. He has a long list of articles, something like 400 papers. I don't know how these people write these number of papers. He has a longer list, it seems, of awards and prizes. The Dirac Medal and the Michelson Medal and the Lorentz Medal, all ... culminating in this year's Nobel Prize, which was given to him for his tweaking, his alteration, his better improvement of an understanding of the strong force, the way in which the quarks bind together in, for example, protons and neutrons. So please welcome this evening a wonderful speaker and a wonderful physicist, one of the leading lights in the world, Frank Wilczek from MIT.
Thank you. I thought it would be fun, certainly for me, to talk tonight about some of the things I'm actually thinking about these days, which are not so much what we already understand, but what we don't understand. So I'm going to talk about 4 big open problems in understanding the universe. Before getting carried away with that, though, I'd like to emphasize that we know a lot. And you have to respect what we know and think about what we don't know. We know in remarkable detail and depth, I think, what ordinary matter is made of and how it behaves in a way that wouldn't have been possible, was inconceivable 100 years ago. And we can summarize it fairly shortly. Matter is made from electrons and photons, and you probably learned in high school that it's made from nucleons, that is the word physicists use for protons and neutrons, but that's really wrong, or at least inadequate. What we've learned over the course of the last 50 years or so is that really a deeper understanding is that the more elementary objects, and as far as we can tell, ultimately elementary objects, are quarks and gluons. It's often said that quarks and gluons can't be seen as as individual particles, and that's true. But nevertheless, here before your eyes is a picture of quarks and gluons. You don't see them as single particles, but you see them as imprinting flows on the particles you do see. And our theories allow us to predict in complete detail how likely it is that you'll have 3 flows versus 4, how likely the different distributions in angle and energy among these flows are. And so we can say with complete confidence that these really are quarks and gluons underneath the visual appearance of things, setting the directions of the flow by equations that we can write down. And we can go further and actually calculate, based on the fundamental theory, the masses of particles, based on building blocks that are essentially massless quarks and truly massless gluons. Those are the basic building blocks. So we start with a theory that has essentially no mass at all, and from that compute with very few parameters. You see 3 things here are used to fix parameters. The rest are calculated by massive computer simulations that solve the equations of the theory, that you calculate the masses of the different particles. This is in my opinion, one of the great scientific achievements of all time, because one of these particles, N, stands for nucleon. This is neutrons and protons, the basis of ordinary matter, and we understand how the mass of ordinary matter arises out of massless building blocks, quantitatively. But for future use, in this lecture, and probably for the future of physics, the most surprising and far-reaching discovery, I would say, of the last 50 years, may be that what appears to us as empty space is in reality a wildly dynamical medium. If you believe in the theory of evolution, this shouldn't surprise you. Our eyes are adapted to look at changes, things that change in the world, things that are useful to survival of ourselves and propagation of the species, so things like saber-toothed tigers and potential mates. Whereas getting a deep view of the microscopic structure of empty space, that is, the things in between the saber-toothed tigers and the potential mates, is not so crucial. It, in fact, would be quite distracting if we could watch it all the time, because this is what it looks like. If your eyes could resolve distances of 10 to the minus 13th centimeters and times of 10 to the minus 24th seconds, this is what you'd see all the time, these quantum fluctuations in the gluon fields. This is not an artist's conception or an engineering design for a lava lamp. What this is looking inside those computer calculations that I showed you gave an account of the masses of protons and neutrons and other particles that have been discovered, to see what's happening, what's the dynamics that's behind the generation of mass from massless building blocks. And this is what the computers are doing. These are the gluon fields fluctuating in what we perceive as empty space. So we get a very profound understanding of matter. Dirac, back in the 1930s, with the origin of modern quantum mechanics, said that now we understood all of chemistry and most of physics. But I don't think that was justified at the time, but I think now it is. Now we understand really the profound origin of chemistry and the physics of ordinary matter in a way that probably won't change for centuries, if ever. It's that profound and quantitative. I mean, I showed you the data. Okay. But just as we got this all sorted out and convinced ourselves of this understanding, the astronomers threw us a big curveball. They told us that what we were understanding was only 5% of the total mass of the universe as a whole. It dominates our local environment. You know, you and I are made out of this ordinary matter of protons, neutrons, or rather, quarks, gluons, electrons, and photons, and it dominates the mass of the Earth, even of the solar system. But when you average over the vast empty spaces, where ordinary matter isn't, but other stuff, as we'll see, is, those empty spaces are so vast that the space between the stars and between the galaxies is so vast that even stuff that's relatively diffuse adds up and comes to dominate the mass of the universe. So the 5% that astronomers have been studying, what astronomers have been studying for 2 or 3 centuries, stars, galaxies, nebulae, comets, all that stuff, is all ordinary matter. That's 5%. In the last 20 years or so, they've discovered the other 95% of the mass. There are 2 contributions to it, and these are 2 of my 4 open problems, namely, what are they? One is called dark matter. So 25% of the mass of the universe as a whole is in some mysterious thing called dark matter. And I'll tell you in the next couple of minutes basically all we know about this dark matter. It's sensed not through it's called dark, but it's not really dark. If it was dark, that is, if it absorbed light, we could study how much light it absorbed and learn a lot about its properties. But it doesn't give away its secrets that easily. It's completely transparent. The only way it's been detected is through its gravitational influence on the kind of matter we can see. And that allows us to figure out the distribution of this dark matter. And we find that it clumps, but not as tightly as ordinary matter. So ordinary matter forms galaxies, say yay big. And every galaxy that's been studied carefully turns out to be embedded in a dark matter halo that's much more extended and diffuse, but the matter is here. So where the ordinary matter is, it's most of the mass, but where it isn't, it's not. And the other stuff fills much bigger spaces. So we know it clumps, but not as tightly as ordinary matter. Recently, astronomers have even found galaxies that don't have stars, don't have ordinary matter that lights up, but is all dark matter. You can see it bends the light from galaxies behind gravitationally. What is the dark matter? Well, I told you I was going to tell you everything we knew about it, and I did. That was it. We don't know. We'd like to know what it's made out of. Is it we haven't seen it interact with ordinary matter or photons. None of the standard tools of astronomy have, or none of the standard instruments of astronomy have enabled us to probe its properties. We'd like to know, is it made out of particles? What do those particles weigh? Do they really not interact at all except with gravity, or just that we haven't used powerful enough instruments? We'd like to know in that kind of detail what this dark matter is. We'd like to understand it as deeply, ideally, as we understand ordinary matter now. How do you think about a question like this? Well, one way is to do experiments. And, of course, people have pursued that. But as I told you, that's been very frustrating. the dark matter so far is transparent in a very strong sense. It hasn't interacted in any way, except through gravity, with ordinary matter. It hasn't emitted light, hasn't absorbed light, hasn't deflected cosmic rays, nothing. But there's another way, which has a great tradition in physics, which is to try to improve the equations of the theories we already have. For instance, back in the 1860s, James Clerk Maxwell studied the equations of electricity and magnetism and found that he could improve them by making a unified theory that made the equations more beautiful and more consistent. And when he did that, when he improved the equations, he found that things came out that weren't in the original equations. What came out in that case were what we now call electromagnetic waves, which is the way we understand light and the way we understand radio waves, which hadn't been imagined at that time. Similarly, Paul Dirac in the 30s looked at the equations that were being used to describe electrons, saw in quantum mechanics, saw that they didn't obey the special theory of relativity, improved the equations by making them consistent with both quantum mechanics and special relativity, and with the improved equations, predicted the existence of antimatter, positrons, which was soon discovered. And my work similarly led to the prediction of gluons, which were subsequently discovered. So it has a long history of success that you try to improve the equations and they cough up surprises. This is relevant to the dark matter problem because we think we understand matter in extreme conditions based on our profound understanding of ordinary matter. I should say ordinary matter in extreme conditions. So much so that we can make sense of this. What you see here is the experimental recreation of conditions that haven't been seen in the universe, as far as we know, since 10 to the minus, about a second after the Big Bang. This is created on Long Island at the Brookhaven National Laboratory, the so-called RHIC accelerator, relativistic heavy ion collider. And what's done there is gold nuclei are accelerated to high energy, crash together in the center here, heat up to enormously high temperatures, reproducing 1 second after the Big Bang, and boom, things come out. Now, if we didn't have any theoretical understanding or expectation, it would be very hard to make sense of this. But we think we have an understanding of matter in those extreme conditions, which enabled us to make predictions for how many particles would come out, how many particles would come out with different energies, and that's what happened, basically. There are a lot of interesting details that weren't anticipated, but broadly speaking, it confirmed our prejudice that we had a good enough understanding of matter to understand the very early universe. And that means that if we improve our equations, we can calculate the cosmological consequences of them and see if, as a byproduct of improving the equations, maybe introducing new particles, we've produced something, we've predicted a particle that would be produced in the Big Bang and has the right properties to be the dark matter. A particularly promising line of ideas along in that direction runs from the idea of trying to unify the different observed interactions of nature by imposing a higher amount of symmetry. To do that requires yet a higher amount of symmetry called supersymmetry, and supersymmetry predicts the world is twice as big as what we thought it was and produces a dark matter candidate. Now, I won't be able to do justice to this in detail, but let me give you kind of a flavor of it, which I can do very shortly. We have beautiful theories of the electromagnetic, the so-called weak, and the strong forces separately. Those are the three basic forces of matter, together with gravity, which I'll come to in a moment. But these interactions are described by mathematically quite similar theories, so-called gauge theories. So the deep mathematics of these is very similar in our although the physical manifestations are quite different, and it's been a fantastic story how from similar-looking equations you can get such different consequences. But in any case, after a lot of work and a long story, you find that they can be described in a common language. The language is the language of symmetry. And once you know that, you're tempted to try to make a more encompassing theory with a larger degree of symmetry that would have all these observed interactions as different consequences of one more fundamental interaction that underlies them all, one ring that rules them all. There's a problem with that, though. If you use the observed values of the couplings, if the interactions are really going to be symmetric in this sense, they have to have equal strength. But they don't have equal strength. As you observe here, the observations are on the left-hand part of this curve. They have very different strengths. But remember, I told you the most profound lesson, perhaps, of recent physics is that the empty space is a dynamical medium. Now, if you think about where unification might occur, we would really think that unification should occur at the very shortest distances, or equivalently, in quantum mechanics, the very highest energies. And even if there is true unification of the interactions at these very short distances, we, viewing at relatively long distances, are looking through the cloud, the clouding effects of this dynamical medium. That lava lamp I showed you before changes what's the fundamental interaction, dresses the particles, we say, and gives them structure that they don't have at the most elementary levels. You have this little thing which causes a disturbance in the vacuum, gets changed in its observable properties if you look at it with relatively crude resolution. But by following the equations out to much larger energies or shorter distances than we can actually measure, we can penetrate those clouds in our minds and see if the observed values of the couplings could have traced after distortion by the dynamical empty space from a unified theory at short distances. If you do that, using the effects of quantum fluctuations due to the particles we know about already in the so-called standard model, you find that it almost but not quite works. You almost get a unification of these different strengths of interaction, but not quite. But if you up the ante by demanding not only that the different interactions unify, but also that particles of different spin unify by extending the symmetry of special relativity, or this is going to sound very mysterious, but maybe we could elaborate on it in the questions, by introducing extra quantum dimensions in addition to the 4 dimensions of space-time we know about. If you take that step, improving the equations not once but twice in different directions, then everything clicks into place and the unification really works. Furthermore, if I put gravity on this same plot, you would find that gravity starts out much weaker than these interactions, but also changes with distance. Its strength changes with distance. And you would find that it too unifies. So this is a grand vision of how we might achieve a unified or nature is pointing us towards a unified interpretation of the apparently very different forces of nature. But remember, we had to extrapolate by many, many orders of magnitude down to much shorter distances than we can actually resolve experimentally, or much higher energies. Fortunately, so we can't test these ideas directly, but fortunately they have indirect experimental consequences. Remember, to make the calculation really work, I had to go to the supersymmetric version. that involved introducing many new particles. Improving the equations has a price in introducing many new particles that haven't yet been observed, basically doubling the world of particles. And where are they? Well, before I tell you where they are, let me say that one of these particles turns out to have the right properties to be the dark matter. It is produced roughly enough in the Big Bang. It lives a long time. It interacts very weakly with matter. It has all the properties that dark matter ought to have. It could be the dark matter if these speculations all hang together. The particles, this world of particles we had to introduce to improve the equations, including the candidate dark substance, can't be too heavy. In fact, for that calculation to work, for these particles to do their job in changing the structure of empty space, and thereby altering the couplings we actually observe in the right way, they can't be too heavy. And in fact, they can't be too heavy that they can't be so heavy that they'll escape observation at the next great accelerator that's being built at CERN near Geneva, the so-called Large Hadron Collider, or LHC. So that machine is being built right now. It will start to operate in the summer of 2007, and on the time scale of 3 to 5 years, we'll know whether this new world of particles and the dark matter it implies is really the right thing, or just whether these apparent successes and coincidences are a big joke on the part of the creator. A cruel joke, I should say. So that's dark matter. I won't go into so much detail on the 3 other open problems, but I wanted to give you that one because it's particularly ripe right now. Dark energy is 70% of the mass of the universe as a whole. So 5% was ordinary matter, which we understand very well. 25% was dark, so-called dark matter, which clumps, which we don't understand but have at least a candidate for understanding. 70% is in some even more mysterious thing called dark energy. It is evenly spread. It doesn't clump, as far as we can tell, as if it were an intrinsic property of space. Something that is the same everywhere, if you think about it, is just a property of space. It's the same everywhere. So empty space, space we perceive as empty, the astronomers perceive as actually having a bit of mass. And furthermore, the strangest thing about it, that's unlike the dark matter, is that it exerts negative pressure. The negative pressure has been inferred by very recent observations, really over the last 5 years, but they've won now the allegiance of all competent observers, that the expansion of the universe, instead of slowing down, as it should be due to gravitational attraction, is actually observed, when you look far out, to be accelerating. The expansion is getting faster. And the only known explanation of this is that there's a negative pressure filling the universe. Positive pressure pushes things together. Negative pressure blows things apart. And that negative pressure is inferred from the universal acceleration. It's also, since it's everywhere, it's a property of empty space. It goes together with the mass density. The total mass density is inferred from the non-bending of space. Okay, if space has positive curvature, like a sphere on large scales, that would mean you have a large density of matter. If it has a so-called negative curvature, so it looks like a saddle, that would give a rather relatively small total density of matter. The non-bending, the apparent flatness of empty space, gives you an intermediate density that you can calculate. And then the amount of dark energy is inferred by subtracting off the dark matter and the ordinary matter, which you can count up by looking at how, in the case of ordinary matter, by adding up the mass of all the things we observe. In the case of dark matter, by adding up its gravitational, the mass that is revealed gravitationally. And the remarkable thing is that this negative pressure is quantitatively related to the mass density by this equation, pressure equals minus rho times c squared. This should be reminiscent of E equals mc squared. At least the c squared is the same. And it really embodies the same, a very closely related kind of physics. E equals mc squared is the equation, the relationship between a mass and the energy of a particle, something that's point-like. P equals minus rho c squared is the relationship between pressure and energy density that's consistent with special relativity for a uniform distribution of either density or pressure. That is, if you have all through space, everywhere, a positive density and a negative pressure related by these equations, then if you do what special relativity tells you to do, namely move past it at a constant velocity, it looks the same. Okay? What looks to an observer who's stationary as, say, just mass, when to an observer that's moving along would look like a combination of mass and pressure. And if they satisfy this equation, then both observers will report the same properties for empty space. So what is the dark energy? We don't know at all. How do you think about a question like this? Well, you can do experiments, but again, so far, even more nothing, because it doesn't even clump. It's just the same everywhere. And the desperate alternative is to think. And we're still thinking. But there is an interesting aspect to this, which is that, in some sense, we've been expecting this for a long time, that empty space should weigh something. Remember, again, I come back to the most profound, the basic lesson, maybe the most surprising lesson we've learned from the physics of the last 50 years, is that empty space is a dynamical medium. Well, if gravity measures all forms of energy, which is what Einstein taught us in general relativity, then it should sense this dynamic, sense all this structure. And when we estimate how much empty space should weigh, the problem was not that it turns out to weigh a little bit. The problem has been for a long time, why doesn't it weigh much more? In fact, if you do crude estimates based on how much structure we observe we reliably infer in empty space, you find that you estimate that the density of empty space should be, well, either infinite, which is certainly much larger than is observed, or maybe 60 orders of magnitude more than we observe. That's 1 with 60 zeros following it, which is an almost inconceivable, it's much, much more than the number of atoms in the universe. No, it isn't. It's comparable to the number of atoms in the universe. Or, well, in any case, certainly much more than, some ridiculously, much more than it does weigh. So most theoretical physicists, seeing that they got an answer that's much smaller, that's ridiculously large, inferred that the correct answer must be 0. In fact, I had a very interesting discussion with the famous physicist Richard Feynman about this, he told me about his early career. He was already worried about this problem, which few people were back in the 1940s. He said, in quantum field theory, well, he said this all with a Brooklyn accent. So in quantum field theory, you have all these vacuum fluctuations. I didn't really want to believe them because empty space is empty. So that's why I understand why it doesn't weigh anything. It's Doesn't weigh anything because it's empty. But his equations didn't agree with that intuition. He told me that was the very disappointing thing. He thought his way of looking at quantum field theory was fundamentally different from the standard way. It turned out to be mathematically equivalent and to have all this structure in empty space, despite his early intuition. So neither Feynman nor anyone else has a real explanation of why, ever came up with an explanation of why it should be zero, although that seemed to be the right answer for a long time. It's fortunate because now the astronomers seem to be telling us it's not quite zero. They've observed both the rho and the p, and they do seem to be connected by this equation. So the tentative conclusion is that ether not only exists, but weighs, just not very much. And that's where we are. We don't understand in any more depth what it is, just that it weighs a little bit, much, much less than it ought to. Still, that's enough to cause trouble. It dominates, as I said, the mass density of the universe, and that negative pressure means that the long-term history of the universe is really unfortunate. Things are going to blow apart. It'll get very cold, very lonely. Galaxies isolated by vast distances, unless something changes and this ether turns into something else. But at present, it just seems to be that doom. Okay, so now I'd like to talk about two other puzzles of a rather different character. This is not what the world is made out of, but why does the world cough up complex structures? This gets more to the questions of evolution and emergence of structure. And from the point of view of fundamental physics, this involves some highly unlikely conspiracies. Because lots of things can go wrong when you try to make nice, user-friendly nuclear physics and chemistry, starting with our standard ingredients. That is, what we now know are the right ingredients, the quarks, gluons, electrons, and photons. For example, if protons or electrons were just a little bit heavier, atoms would degenerate into neutron matter. The protons and electrons would find it energetically advantageous to combine into neutrons, and you'd have no atoms, no chemistry, just neutrons. That would be hard to live with. If neutrons were a bit heavier, then deuterium would unbind, and if you track through the Big Bang and the origin of elements, you'll find that no elements heavier than hydrogen would arise. And again, this would be a very difficult world to support complex chemistry. You'd get a lot of H2 molecules, but that's it. You can make this quantitative, and I won't try to do justice to this graph, because maybe not all of you are comfortable with it, but I can just give you the visual impression. Here's our world with a particular value of the electron mass and a particular value of the difference between the up and down quark masses. If you get outside this triangle here, then you have the disasters I told you about. In this direction, you get only protons. In this direction, you get only neutrons. And those would be catastrophic. What makes this disconcerting is we don't know, even remotely, why the value of the electron mass and the value of these quark masses are what they are. They seem to be finely tuned to allow the emergence of complex chemistry, complex nuclear physics and chemistry. That's one example. There are numerous examples of this apparent fine-tuning among the fundamental constants to enable complexity. Even if your microscopic laws enable complexity, however, there's a question of whether complexity actually emerges in the evolution of the universe. Lots of things can go wrong when you try to make nice solar systems in the way we think the universe actually makes solar systems. The Big Bang is approximately, to a very good approximation, we see in from the microwave background radiation, which tells us about the early distribution of matter, was very, very nearly homogeneous. There were tiny seeds, part in 10,000 little fluctuations from from accurate homogeneity, which grew slowly by gravitational instability. Where it was denser, attracted more stuff, and so it got still denser, and that made an instability. And those small seeds eventually grew into galaxies, and then solar systems, and planets, and people, and so forth. That's the broad brush picture of emergence of structure. And you'll hear a lot more about it if you go to follow the subsequent lectures, but I don't think they'll make a liar out of me. That's the picture. But lots can go wrong. I'll show you some of the things can go wrong. First, the ordinary matter might fail to cool. You see, it's going to fall into these gravitational wells, but if it can't lose energy, the particles just fall out again. They'll slosh around. And we know this can happen because this is what's happened to the dark matter. It's remained diffuse. It hasn't settled down into compact objects. And you can calculate, as a function of what kind of fluctuations, what kind of objects are emerging from cosmology, which ones would be suitable to have matter that cooled and could form condensed structures, so that the protons and neutrons would be able to find each other and make complex objects like planets and stars. And the cooling only occurs outside of this yellow region. I won't attempt to do justice to the details of this plot, of course, but roughly speaking, this axis shows the escape velocity, what velocity particles have to get out of the fluctuation. This one shows the density. Okay, so if the escape velocity is too small, that is, if the object is not very much bound, or if it's not very dense, then this cooling can't occur. So if it's too yeah. Another problem is if the escape velocity is too large, then your fluctuation will just form a giant black hole. Also not favorable for life. And that rules out this region. Some of this region here is doubly ruled out because it was already. Another thing that might go wrong, the matter might get swept away by the first supernovae. Okay, so you might have a promising galaxy, you might even form stars, but the first stars that go supernovae release an enormous amount of energy. If the binding energy of the matter inside the fluctuation is too small, all that gas will blow away. You'll never form a second generation of stars. This means you'll never have heavy elements, which are produced in the stars. They'll never have a chance to form, and again, you won't be able to form complex chemistry. That rules out all this. On the other hand, if things are really dense, then the things that do in the dinosaurs might do in any life that started to exist. If things are really dense, stars have frequent encounters which disrupt any potential solar systems, and again make life terribly difficult, or certainly the emergence of intelligent life very difficult. So if there's no safe haven from disruptive encounters, that also doesn't make a user-friendly galaxy. And you see the region where you have user-friendly galaxies like ours, this star, is getting very small. And in terms of the fundamental parameters, well, so that's a conservative estimate. If you're willing to live a really hard life, you might be able to live in this blue band, or if you evolve really quickly. But if you take a leisurely time and want to have a nice, stable solar system without too many Cretaceous events that wipe out most of life, then you don't want to be in here either. And you see there's just a little region left. So to avoid all these pitfalls, things have to be just right. First of all, this dark matter density, which causes the universe ultimately to blow up, better not be too big, or the universe would have accelerated long ago and would have been, it would have blown apart the galaxies before they could form. And also, when you work it out more quantitatively, there has to be a relationship between the dark energy density, the amplitude of the initial fluctuations, how big they were. In our universe, they're, I said, a part in 10,000, and the amount of dark matter you have. That's shown here with something I call Tegmark's banana. Max Tegmark, a physicist at MIT, one of my collaborators, worked this out. Basically, what gets formed are the darker green regions, and depends on these fundamental parameters. You'd better have a substantial overlap between these dark green regions and the sweet spot where intelligent life can emerge if you're going to have a universe that works. And this only shows one choice of those parameters. If you change the parameters, make the amplitude larger or smaller, you move this banana up or down. If you change the dark matter along these diagonal lines, if you change the dark matter density, you move up or down this way, and you very easily can move the banana outside the sweet spot. So there are conspiracies both among the microphysical parameters, that is the quark and electron masses, and the parameters of cosmology that seem to be pretty exquisite to get complexity as we know it. So that's raised in recent physical speculations the idea that there's actually not just the universe we observe with the laws we observe, the same everywhere so far that we've observed it, but actually we've observed only a small part of a much bigger universe. And the reason that our universe has these conspiracies that support life is that those other regions don't have the conspiracies, they don't have life, no one's there to observe it. It's a new kind of argument. Well, some nuts have been making that kind of argument for a long time, but it's a new kind of argument in respectable circles in physics. Or maybe there's not selection. That's the alternative. Now, I scare people when I say design, but what I mean here is design in the sense of Einstein. And I'll just close by reading what now appears to be a charmingly innocent statement by a physicist of the past. I would like to state a theorem which at present cannot be based upon anything. Well, you can read it. But the basic idea here is that God had no choice, or there was no choice in making the universe, that these conspiracies were dictated by some consistency principle or symmetry or dynamics. But it appears now that, well, maybe it'll work out that way, but the way the wind seems to be blowing is that they really do seem to be conspiracies. And as we've understood physics better and better, they still seem to be conspiracies. And so we're getting desperate and maybe thinking we have to invoke selection. Okay, thanks.
Okay, that's a fine beginning. Though in my gut I would have liked to terminated that before the penultimate slide. But we'll get back to that in the panel. So let's go directly to our second speaker now to have a bit of a contrast, to move a little bit perhaps along the arrow of time. Colin Norman is a good old friend from Johns Hopkins, a friend and perhaps co-conspirator in the days and months and years leading up to Hubble's launch. Colin is a senior professor of physics at Johns Hopkins and across the street a senior astronomer at Space Telescope Science Institute. He hails originally from Melbourne, where he took his undergraduate degree, then on to Oxford as a Rhodes Scholar, where he took his doctorate. He's taught at a number of places, but for the past 20 years or so, he's been at Johns Hopkins. He's also got an incredible number of papers, well more than 200 in the published refereed journals. He's done a wide spectrum of astrophysical work with objects that seem to be explosive, whether they be accretion disks of holes or gamma ray bursters or a wide variety of. I remember reading some of his earlier papers on interstellar masers, when I was coming up through the system here in the 1970s. So let's not hesitate at all and go directly to our next speaker. Please welcome Colin Norman from Baltimore.
So, it's on. Great, but I need it up here. Thanks. I need to push the buttons. That's great. Thank you very much, Eric. Those were great days. Incredibly character-building days when we had to explain to a Senate review panel why Hubble didn't work. And then we had to, in fact, ask for, they said, well, how much will it cost to fix it? And we said, only $1 billion. So it was quite fun. Yep. I'm trying to explain something in the next half hour about galaxy formation and evolution. And I thought I'd show a galaxy first. So here's M83, magnificent spiral galaxy. Our galaxy is quite like this, but it has a little bit of a bigger bulge and somewhat more open spiral arms. But just to set the scene, where if we were living here in this galaxy, we'd be out here on the edges of the galaxy, around about 10,000 light years out. In the lifetime of this galaxy, our sun would have rotated around something like 30 times. Okay. The rotation time is 300 million years, and the age of the universe I'm taking is nominally 10 gigayears. And the time, let's just look at a little bit at this rotation. So I said 300 million years to go around, and then think if we take a conservative estimate for the time with which we have been doing, what we might call modern science, and we would say it was very, very conservatively 10,000 years, then we have only rotated about to there. So we're this tiny speck of dust on the edge of a beautiful galaxy, and we're trying to understand something like this, the entire universe. And as Frank has beautifully explained, there's many magnificent problems about this. I'm going to tell you some things that we have actually found. But I should also say that when I go out the door in the morning sometimes, and this is echoing the 5% of baryons in the universe, my children say to me, Dad, why are you even bothering to go to work? Because you're only working on 5% of the universe. So anyway, we start with the Big Bang. The universe is extremely hot, and then as time goes by, it cools. And it cools from a hot plasma, electrons and protons, down to a nice neutral plasma, and this occurs at about 1 million years. And then there's a long time called the Dark Ages in which nothing happens. Nothing at all. There's no star formation, no galaxy formation. It's just a big ocean of neutral hydrogen. And telescopes are being planned to try and observe this, but if nothing's happening, it's really difficult. So then after some time, at what we call probably at about a redshift of 20, and I should say what redshift is. Redshift is essentially the amount that the wavelength of a spectral line, the wavelength of, say, the hydrogen line at 21 centimeters, or any other line that you like to think about in the hydrogen atom, is shifted. So the relative shift in the wavelength relative to the center of the line is the redshift. So at a redshift of about, let's say, 20, and I'll show you simulations of this, the first stars begin to form. And then, and why do they form? They form because there are fluctuations which have been imprinted in the universe from the very beginning, which grow slowly over time. They grow slowly over time because the universe is expanding. If the universe wasn't expanding, these fluctuations would grow extremely rapidly, but because it's expanding, they grow slowly. And Why we know so much about these fluctuations now is from the beautiful work of the satellite called WMAP, which managed to measure the level of fluctuations and deduce many parameters of the cosmological parameters of the universe from looking at this surface here where the universe recombined. Okay, so you're looking at fluctuations here and measuring them, and they've been imprinted from the Big Bang, but this is the first place, at least currently, that we can measure them using radio telescopes. And these fluctuations are allowed to grow from about here onwards, and they grow sufficiently to become nonlinear and form the first stars, then those stars, and then the first galaxies. And then the general cosmology that I'm going to talk about, galaxy formation, comes in. And one of the major observations that I'm going to talk about come from the Hubble ultra-deep field, where we can begin to see galaxies, interesting properties about galaxies, not just isolated properties, but statistical properties about galaxies, now at about a redshift of 6. When Eric left Baltimore in 1992, this was a very unfortunate event, of course, because he used to sit next to me at operatic meetings run by Riccardo Giacconi, and he would write down, I thought he was working on something else, but he would write down everything that was going on. It was most interesting. Later, some of it appeared in a book. I'm losing this. Okay. So the Hubble. So when Eric left Baltimore in 1992, no one would imagine that we could get what's called the luminosity function of galaxies, for example, at redshift of 6, which is where the Hubble deep field goes out to, the Hubble ultra deep field. And so I'm going to proceed reasonably rapidly and tell you about how galaxies form and evolve on the basis of some of the observations and some of the simulations. This has been gone over by Frank, and it's slightly blurred. I don't know why, maybe because our understanding is a little bit blurred. But dark matter is about 30% of the universe. Dark energy is about 70%. I think the guys don't like it up there. First, I'm going to turn off the laser pointer. Wait. Was this need to be connected? Okay, I'm going to take this off and just swap it, man. Well, you see, something is happening. All right. Here,
We'll switch to the red one.
Yeah, whatever you like. Give me that one.
Oh, the red one. He's going to go to the red.
Very good. It's on now? Yep. So you can see why my children worry about this, because that little band there is just, that band there is 4% of the universe, and the rest we know little about. Okay. What? This is ridiculous. I've never had so much trouble. Do you think it's because I'm in Boston? My children said, "Don't even go there, Dad. The Red Sox play there." Okay. So a long time ago, when the universe was about 1/20th of its current age, a very interesting event occurred. Probably a massive star collapsed, a central black hole was formed, and an enormous pulse of energy in gamma rays called the gamma ray burst, lasting about 10 seconds or so, was sent out from this object. And we saw it, or at least the observers here on Earth, and with the satellite orbiting the Earth, saw it last week. And so this is the formation of a black hole of the order of, a solar mass, maybe it's 10 solar masses, in the region that I'm talking about where galaxy formation began, and that's about redshift 6. And this is an amazing new discovery. We think that black hole formation like this, with probing the universe with gamma ray bursts, and looking at these black holes forming at redshift 6 is going to become relatively easy, and one can see them even out to redshift 10 with current instrumentation, and I think it's just a matter of searching for them. But this is a relatively, we get a new discovery in astronomy about every month, but this is the one from last week, relevant to this subject, which is really quite interesting. And I submitted the paper about it on Sunday night. Okay, now the universe is neutral. It's basically, until something happens, some stars form, some galaxies form, then it's essentially doing nothing. So stars form, galaxies form, and the regions around these stars and galaxies, and this is an artist's impression, begin to ionize the medium. And we know today that the medium's ionized, and from the WMAP results, which have enormous error bars, we know that the universe was ionized somewhere between a redshift of about 10 and 20. And it goes like this. The physics of actually understanding how to do the ionization calculations in the universe is very difficult, even with current large computers, and is a subject of much current research. So we think we can reionize the universe with the available stars at about a redshift, around 10-ish. The next thing that I wanted to talk about is how we measure the acceleration of the universe. We do that currently using type 1a supernovae, a special sort of supernovae associated with a sort of a standard mass compact star called a white dwarf. And we look very carefully, or people look very carefully at images of galaxies on a routine basis and find little things here, like supernovae. And you'll see why we need a space telescope. You'll see here, this is before the supernovae, then afterwards, before, afterwards, etc. If you don't have a high-resolution telescope such as Hubble, then this supernova gets embedded in the general light of this object, and there's no other way currently to find supernovae. So you need Hubble or some better version of Hubble to find these supernovae. And there are plans made to fly, very expensive of course, missions in order to get many, many supernovae and try and understand the acceleration of the universe. And this is the diagram that one has in one's mind about what these what we can learn from studying these supernovae. The universe is our current... Oh, I can't believe this. Why is this happening? I think it's a Boston conspiracy. I'm never coming back. Okay. So, the universe probably does something without a lambda, without a cosmological constant, the sort of thing Frank talked about that is small but important. It would do something like this. But with the cosmological constant, you can see that it starts from the Big Bang, decelerates, and then begins at very large distances to accelerate. And one can get images, one can get determinations of the acceleration in the universe by plotting these type 1a super results, type 1a supernovae results, and analyzing the expansion. There are many other ways to determine the expansion of the acceleration of the universe, but they are not quite as mature as the supernova type 1a results. Okay, here's a magnificent spiral galaxy from the Very Large Telescope at ESO in Chile, and this is NGC 4565, and you can see dust lanes, a beautiful bulge, etc. But when we look at the dynamics of this galaxy, it is observationally, unambiguously determined that this is just a small fraction of the dynamical mass. And you then, let's say, if you go from about here and go out by a factor of 10 in both directions, then that will be the radius of the actual galaxy, and that is all made of dark matter. So again, we're just seeing the froth on the dark matter distribution, even with such magnificent luminous things such as this wonderful edge-on spiral galaxy. Now, I mentioned the Hubble Ultra Deep Field, and this is it. We're looking deep into space, and the very faint objects are little galaxies forming at up to redshift 6. And there are many interesting things about this slide. I'll show you a couple of details. The first is that the galaxies are often disturbed and distorted, okay, as you can see. And but you can begin, in some cases, to see significant structure. Okay. What one learns from this, and one's learned the same thing from many other calculations. So number one is that many galaxies are disturbed, distorted. They look like they're interacting and colliding. And it does look like the great models that have been made over the last 20 years of cold dark matter, halos with appropriate gas dynamic physics, where it's sort of a bottom-up approach where you make the small things first and they build up and make the bigger and bigger galaxies. This looks like it has some significant validity if we look at all the merging and interaction that's going on at high redshift. There are some well-known, at least in the field, potential problems with this, but I won't go into them at the moment. But generally speaking, the overall framework is reasonable. Okay. The star formation history of the universe is interesting. Previously, one thought the star formation, and this is time, and this is sort of star formation. And one thought that it went up and then came down. But it looks like there's a lot more star formation at early times than we previously thought. And this is going up to something like redshift 6. So here's the Big Bang, the dark era, the Milky Way's forming about here, our solar system's forming, life, etc. It's a bit like Eric's slide. And here's the star formation history of the universe. So it peaks, if it peaks at all, it peaks early. And this has been a big change in the last 15 years or so, to realize that many things happened relatively early in the universe. Now, locally, we see many examples of these colliding and interacting systems. Here's an optical image of the antennae where the two galaxies are colliding. There was a great and classic paper written by Alain Toumre from MIT explaining this in detail, and then he generalized it in a really profound intellectual leap that all galaxies may be made this way, that you're colliding two massive spiral galaxies here, and this is the central region of these things with all sorts of blue stuff, luminous blue stuff here, where star formation is going on. And this is the mode. Think of this as pretty much the mode by which all galaxies are forming. This is the very central regions where one's got a luminosity in this object which is enormous. It's not quite quasar-type luminosities, but it is enormous, and it's all coming from star formation rates where you're forming 100 solar masses of stars every year. And in this one, this is an X-ray image of such a region, a central region of where you're forming 100 solar masses per year, and this is from ARP 220, and there's most likely a black hole and a black hole which is being fueled at the center, but much of it is being obscured in the optical anyway by this by the large amount of gas in the region. But this is X-rays, so this is very hot gas, and enormous super winds come out of the central region of these colliding and interacting galaxies and pollute the intergalactic medium with metals and pump in energy and reheat it and give substantial amounts of entropy to the medium. This is another one, NGC 1569, which is again a diffuse small galaxy, which we see locally starbursting, but it is typical of what we would see if you look carefully at high redshift. And this is the Chandra Deep Field, which I had great pleasure working on for a while. And this is an X-ray image of the sky. So I've been showing you optical images so far, but this is taken in the X-rays. And if you add up all the light from these active galaxies, mostly active galaxies here, there are some galaxies, very faint objects, which also emit low-level X-rays. But if you add up all the light from this, then pretty much this explains the X-ray background of the universe, so that a long-standing problem is the nature of the X-ray background was solved by these observations using the wonderful Chandra X-ray telescope, which is really run in Boston here at MIT and Harvard. What else can I say? In this slide, there are many this is covered with black holes, supermassive black holes, fueling the activity here. And there are galaxies around every black hole. But there are many buried quasars, and I'll come to that in a sec. In fact, right now. So let me skip a slide. Chandra observations are in the X-ray. Hubble observations are in the optical. And Spitzer, the great new infrared telescope, operates in the obviously operates in the infrared, but this can see deep into regions where there's enormous obscuration in the optical. So we're looking at active galaxies and quasars, so the region around black holes, using Chandra observations. We see nothing with Hubble, and yet they're coming out in the infrared. And this is the basis for what people now believe to be the claim that many black holes in the universe are hidden, and that there's a substantial, in fact most in some claims in the current literature, most black holes may be hidden, and therefore we've miscounted the number of black holes in the universe quite considerably, number of massive black holes. I'm now going to show you some simulations. These are the biggest simulations ever done. I wanted to bring an IMAX movie, but then I tried it out again on my children, my teenagers, and they said, "Dad, you can't show an IMAX movie on your laptop. Why don't you get another one, right? A super new Mac, G4 or something." So I'll do that later, right? So 500 megaparsecs is the scale here. I'm starting at redshift 18, and there are fluctuations imprinted. Okay, so if I go reasonably quickly, whoops. So I'm just doing 4 per shot. So this is the large scale. Then I go quickly, and I see the structure of the universe has already developed, the large scale structure, by redshift 0. And what I'm showing you here is the dark matter structure of the universe. Now I'm going to go to a 30 megaparsec scale. So this is much, much smaller than that large scale structure, and you'll see quite remarkable things. So I'm redshift 18. I begin to see little things here, but then by redshift 10-ish, then I begin to see quite significant structures. You can see how stars would be forming, galaxies are beginning to form, clusters of galaxies form at the intersection of filaments, and then as I'm coming down now to redshift 0, this is about redshift 3, then you can see great clusters are forming. Certainly the cosmic web is well in place, or getting to be well in place, and now at redshift 0 you see it. And you can go to even higher resolution. I think there's 10 million points in this simulation. It's run by the Millennium Simulation guys, and I think Volker Springer, who was here, is the first author on this. Okay, so I think we've only got half an hour to go, I believe, so I think I'll just wrap up. We're trying to make galaxies that look like this. Okay, this is an infrared image of NGC 7331. So you can see that there's enormous complexity in here, which we're going to get onto later in the series. This is the central region of 7331, and then there's dust lanes out here, molecular clouds, all sorts of molecules in molecular clouds, star formation occurring in the spiral arms of this great galaxy. And many of the processes which produce the metals, which then go to produce the molecules, etc., 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 are occurring quite obviously in beautiful structures in these vast spiral galaxies. And as this series goes on, you'll be able to essentially learn a lot more about the processes here and decide, things like, is life likely in such magnificent things all over the universe? Remember that there's, in 1990 again, we knew no planets around other stars. We now know somewhere between 100 and 200 extrasolar planetary systems. Remember also that there's 100 billion stars in our galaxy and about 100 billion galaxies in the universe, so that the number of possibilities is quite significant. Okay. And then this is NGC 891. This is a galaxy which is quite similar to ours. It's mostly dust, mostly shrouded by dust. It's got wonderful energy flows going up and down in the system. And one needs, in order to understand galaxies, one needs to understand the inextricable relationship between the star formation processes, the feedback that are going on from star formation processes. In the very center of such galaxies, there lurk black holes. One needs to understand how the energy input from black holes affects the galaxy formation processes itself. And so there's much to be done, as well as understanding the enormous halo of dark matter around this system, and then the vast space, smoothish space, in which it's embedded, which is essentially dominated by the dark energy. So I think we'll stop here and have a good panel discussion. Thank you very much.
Not sure if it's on. There it is. Okay. We're going to take a 1-minute break for you to get up out of your seat and 7th inning stretch in place. Don't leave necessarily, because the panel discussion for many people is the highlight of the evening. So we'll form the panel at this point and be back with you in 1 minute.